To this point, the Modal Shop has made over 3 hours of video content on our portable vibration calibrator, and yet we have never made a video for the test and measurement market. Well, today is the day. My name is Mike Scott. I'm the Industrial Product Manager for the Modal Shop, but today we're going to focus on something different. We're going to calibrate a PCB 357B04 single-ended 10 picocoulomb per G charge mode Excel for the test and measurement market with a plus or minus 5% tolerance to 9 kilohertz. In this video, you will learn how to mount the transducer and connect it to the C9110D portable vibration calibrator, how to load a CalRoute, which is a programmed step sign test with a pass-fail notification after each test point, how to operate the C9110D and execute the test, saving the test points to the memory, and how to create a calibration certificate as well, and we'll show the finished calibration certificate. We do have a separate video to show exactly how to program that aforementioned step-signed CalRoute test and how to create a 17025 compliant calibration certificate. So let's get started. So the first step to calibrating the 357B04 is to apply a little silicone grease. We use Dow Corning DC4 to the top of the shaker. We want to make sure it's clean, make sure the grease is applied, and we want to make sure that the bottom of our transducer is clean. And then we can screw this onto the top. I'm using a 1032 to 1/4-28 stud, as the shaker has a 1/4-28 female hole. Then we use the supplied wrench to secure the shaker's armature, and then we use a torque wrench to apply the proper torque for the calibration of this transducer, and it should be 15 inch-pounds per the manual. Anything from 10 to 20 inch-pounds is fine for the 357B04. Next step is to connect our cable. I got kind of a long cable here, so I coiled up the part I don't need. I'm just going to put it in the pocket of the calibrator, connect the 1032. These can be tricky. You push them in and then twist. And then we connect the BNC to the charge input BNC at the top left, and we flip the charge knob to on. And we're connected and ready to test. The next step in calibrating the 357B04 is to load our pre-programmed step sign test with pass-fail notification and activate it. So I use the frequency dial to highlight the test settings. I go to the CalRoute function and I load a file from my USB that I've plugged into the top of the calibrator. Calibrator will read the USB and give me a list of available CalRoutes or pre-programmed step sign tests. I'll choose the 357B04, and now I need to activate that test. So that joins my list of tests that are stored in the memory of the calibrator, and I can activate it by clicking Activate and choosing the appropriate test. Now I'm locked in to that step sign test. I can't use the shaker in manual mode anymore. If I turn the amplitude dial, nothing happens. I'm locked into my pre-programmed test, which is going to start at 100 Hertz. I can save that test point by pressing the File button. You can see that the sensitivity was 9.84 and the tolerance is plus or minus 15% at 100 Hertz. So anything from 8.5 to 11.5 picocoulombs per G passes calibration. And you see that data on the screen. Now I'm going to sweep down starting at 9,000 Hertz, and you can see the frequency is automatically adjusted to 9,000 and my amplitude is 1 G peak. The sensitivity is 10.08 picocoulombs per G. Now what the calibrator will do is apply a plus or minus 5% tolerance. The rest of the frequency points have a plus or minus 5% tolerance, so I've programmed that tolerance, and it will apply that to the sensitivity at my reference frequency. And my reference frequency was that 100 Hertz test point. So I'm allowed to be between 9.35 and 10.33 based on the measurement that I took at 100 Hertz. And that test point passes. And that's going to be the same for the rest of the test points for this accelerometer. 8,000 Hertz we pass, and now I can go relatively quickly. I'm waiting for the amplitude to settle on 1G peak, and then each time I'm just going to go ahead and hit the file button, and that saves the data point to the memory, gives me the pass-fail screen, and then one more click and I advance to the next test point. So I'm going down in a frequency sweep down in the thousands here, and we're going to stop at 10 Hertz. So I have quite a few more points to go. The amplitude on the screen is the actual vibration amplitude as measured by the reference accelerometer that's in the shaker. So you want to wait for that number to settle on 1G peak or whatever you programmed, and then just make sure the sensitivity also settles. And this transducer has a lot of stability, so it doesn't take very much time to settle. A couple seconds at each test point is all it takes. And now we're down to 500 Hertz. And again, each of these test points, plus or minus 5% tolerance is being applied, but some transducers have different specifications, so you can also apply any percentage that you would like, and it also supports asymmetric tolerances as well. So if you want to test a 10% band, you can go ahead and do that, and the pass-fail will be calculated based on plus or minus 10%. And again, we have another video available to show you how I programmed, specifically how I programmed this test. 30 Hertz is a pass, and this is our last test point at 10 Hertz. I want to point out one thing, that I programmed 1G peak, but at 10 Hertz the shaker is not powerful enough to generate 1G peak. So the calibrator is going to give me the maximum amplitude that it can achieve without causing damage to the mechanical structure of the device, and that's 0.81 G's peak. So it will not allow you to program something that's going to cause damage to the shaker. It'll prevent that and give you the actual vibration amplitude on the screen there and record the data to the memory. So that was a 15-point calibration for the 357B04. All test points passed. Here on this screen we can enter the serial number if we like. I like to do that in the calibration certificate itself, and then we save it to the memory with a date and time stamp, which is ISO 17025 compliant. And we're done. We can pause the shaker and mount another transducer for calibration. All right, the first step in creating our calibration certificate for the 357B04 accelerometer is to open the supplied report generation workbook from the USB drive that is also supplied with the C9110D. And this is a Microsoft Excel macro-enabled file that requires no additional software besides Microsoft Excel. The next step is to click on the Import Data from File button and then go back to the USB drive, open CalRecords_PVC, choose the date on which you exported, the date and time on which you exported the file, and then choose the file. Now my raw data has imported into this data table, but this is not the calibration certificate. My reference frequency is set for 100 Hertz, but I can change that if I'd like. The key is to make sure you take data at the reference frequency. In this case, 100 Hertz is correct, but it can be changed to 159 or 80 or whatever you'd like. Next step is to hit View Certificate, and this is my calibration certificate for the 357B04. Sensitivity at 100 Hertz of 9.84 picocoulombs per G, and a test level of 1G peak. Now your eye is immediately drawn to the calibration line, which doesn't look super great. But what happened is the worst deviation that I had was 2.6% down at 2000 Hertz. And I also had 2.5% high at 10 Hertz and 2.5% high at 9000 Hertz. All of these points passed calibration. They needed to stay within plus or minus 5% of the sensitivity at reference. So since I didn't have any values, the plot is drawn with the worst case value in mind. So since I didn't have any values that crossed the 5% threshold, it drew a deviation plot on plus or minus 5%, which is like a really zoomed in plot with a lot of resolution. So if I want this to just look better, and remember, I'm not changing the data here, I'm just going to zoom out a little bit so we get a flatter line. It's not so eye-catching. And you just do so in Microsoft Excel there by changing your minimum and maximum bounds and your major grid line. And then you can close out of this. Your calibration certificate looks really flat. Although again, I didn't change any data. I just changed the deviation scale over here on the y-axis to plus or minus 15%. From here I can enter the serial number, 3927, manufacturer PCB. I could enter a description of the accelerometer if I wanted, its specifications. I'll go ahead and skip that. You see the notes here, ISO 16063 part 21. I can enter anything I'd like for user notes, customer notes. As found and as left are both in tolerance. So I'm not going to adjust anything here. And I can put myself down as a technician. The date and time shows up here on the bottom right. You cannot change the date and time. That's what makes it an ISO 17025 compliant document. You also cannot change any of the raw data here in the data table. So if you accidentally click somewhere, there's no way to manipulate your data on accident. And that's the calibration certificate for the 357B04. You might be wondering, what's the low frequency response of this transducer? Well, the low frequency response of a charge mode accelerometer is determined by the electronics that you connect it to. In this case, the low frequency limit of the C9110D when calibrating a charge mode accelerometer is 10 Hz. For all other sensor types, ICP, voltage, modulated current, the low frequency limit is 5 Hz. Now that was a single-ended charge mode accelerometer commonly found in test applications, but the C9110D also works for differential accelerometers that you find on turbine engines in aerospace or the energy market, and it's supplied with a cable that mates to the most popular transducers in those markets. For more information on the Modal Shop series of portable vibration calibrators, please visit the Video Vault on our website, as we have many other videos to show you how to calibrate different types of transducers. Thanks again for watching.